All right, let's take a moment to review something that I think you should already know, but maybe have forgotten about. So let's talk about saturation, temperature, and pressure, and then I'll go on to show you what this has to do with fluid mechanics and why we care. Um, so these are really equilibrium properties between a vapor and a liquid. The first one, saturation temperature, describes basically the temperature at which things boil. So that is a function of pressure, right? So at higher pressures, you have to go to increasingly higher temperatures in order to get things to boil. Um, if if you raise the temperature of something above the saturation temperature, then it boils. If you reduce the temperature below the saturation temperature, then the vapor will condense back into liquid. Um, there are, for any particular liquid vapor equilibrium, for whatever the material is, there are tables of saturation, pressure, and temperature that describe that process. So the one that you're most familiar with is probably the one for water. So the key thing is that water boils at 100 degrees C at atmospheric pressure. So in fact, the saturation temperature is the way you would say this is the saturation temperature at a pressure of 101 kilopascals. That's atmospheric pressure, is 100 degrees C for water. The flip side of that is to talk about, and I think this is probably the less understood one, but the more important one for fluid mechanics is saturation pressure. It's really just the flip side of saturation temperature. So at a given temperature, what is the pressure below which boiling will occur? Or the flip side of that is the pressure above which vapor will condense back into liquid. So the saturation pressure at 100 degrees C for water is exactly atmospheric pressure, so 101 kilopascals. A more relevant property that I'm going to show you is important for fluid mechanics is the saturation pressure at room temperature. So at room temperature, what pressure do you have to get to boil water? And that pressure is 3 kilopascals for water. Or equivalently, the partial pressure of water at 25 degrees C, the maximum partial pressure of water at 25 degrees C is 3 kilopascals. Why is that related to fluid mechanics? Well, let me show you an example. So we haven't done enough fluid mechanics yet to be able to predict flow fields or like velocity fields or pressure distributions, but suffice it to say that for example, we'll be interested in flow around wings, right? So if I'm thinking about what happens when fluid, or let's say liquid like water, goes around a fin, for example, at the far field where flow enters and starts to impinge on the fin, very far away, it's ambient pressure, right, at a given temperature, right? So you have ambient pressure, but then as the flow interacts with the fin, certain portions of the fluid will speed up. Maybe some portions will slow down too, but there'll be these portions that speed up. And it turns out that, and we'll show that the faster a flow goes, the lower a pressure it will obtain. And so as a fluid accelerates as it goes around an object, there will be areas of the flow field that have lower pressure. Why is that important? Well, if that pressure ever gets lower than the saturation pressure, then flow can actually boil. So that you're starting off at atmospheric pressure, but as the flow goes around the object, if the pressure ever drops so much that it goes underneath the saturation pressure, then the flow will begin to boil. That generates bubbles, right? So here's a video of a turbine blade spinning, and if you spin a turbine blade fast enough, then the pressure will drop, especially at the tips of the turbine blades. So on the right hand of this side of this video, you'll see these little blades spinning around, and at the tips, the pressure is so low that you actually generate flow-induced boiling, which will create a vapor trail, which eventually breaks into bubbles. And the interesting thing about that is that if as later when the flow gets farther away from those tips, the pressure will go back up to where it was, right? It'll go back up to ambient, but the bubbles will still exist. And that means that those bubbles will have to collapse, right? So it's kind of like the opposite of boiling, right? It's sort of like condensation, but it's condensing back into the liquid rather than on an object. And so that vapor pressure will go back into being a liquid, and that means that the bubbles collapse. What's interesting about that is that when bubbles collapse, they actually sort of release sort of a vibrational pressure wave. We'll never get to the point in this class where we model those vibrational pressure waves, but the thing is that when they collapse, they tend to cause damage to things. So if those collapsing bubbles actually touch the turbine blade or any objects behind the turbine blade, like say a rudder, or maybe your pipe walls, if it's blades that are inside of a pump or something, then when those bubbles collapse, they cause noise and damage. So generally, cavitation is something you want to avoid, and generally we can avoid that via smart engineering. So in the case of turbine, or in the case of propeller blades, you would design the blades to basically distribute the low pressure regions so that you don't have one particular point emitting a vapor trail, or just literally slow down the propeller so that you don't do that. That can have major real world consequences. There's another case where this comes up where I'm not sure how far we'll make it into this course in talking about pumps, but another common place where cavitation occurs and actually does major destructive damage is in pumps. We haven't yet talked about what a pump is or how it works in this class, and I won't go into the details of how a pump works right now. But what I'll just say about it is that basically think about what a pump does. So what a pump does is it takes fluid through an inlet and it spits it out in an outlet. But the key thing about a pump is that it raises the pressure of a fluid. So there's an inlet, a fluid goes into the inlet, and when it comes out the outlet, it has a higher pressure. So let me just make sure that we're clear about a common misconception. Some people have a misconception that a pump raises the speed of a fluid. It doesn't actually speed anything up, in the sense that stuff goes in the inlet and it comes out the outlet. Conservation of mass says that the same amount of stuff goes in the inlet as comes out the outlet. So at least within the pump, nothing actually speeds up within the pump. The inlet velocities tend to be about the same as the outlet velocities. And so what's going on inside the pump is that you're adding some work to things, and that actually ends up manifesting itself as a higher enthalpy or higher pressure. But the way that works we'll talk about later. But suffice it to say that fluid goes in an inlet at a lower pressure than it goes out. You're basically raising the pressure of a fluid. What does any of that have to do with cavitation? So cavitation occurs in pumps a lot for the following reason. Bad design. So a lot of situations you are trying to move a fluid around by raising the pressure, right? So why does that do things? Well, fluid travels from regions of lower pressure, or from regions of higher pressure to lower pressure. So one way to move a fluid up a pipe is to create a low pressure at, let's see if I can get a pointer here. You can try and create a low pressure at an outlet and a higher pressure at an inlet, and that'll drive fluid up. So in this particular case, you'll end up in a situation where the inlet has a pressure of atmospheric pressure minus some amount that has to do with the weight of the fluid that you're trying to pull uphill. So we'll learn later that amount of pressure would be equal to rho, the density, times g times h, but for the moment, forget about it. That the important part is that if you try and pull water uphill, that means that at the inlet, the pressure will be lower than at the outlet. So remember that the pump here is going to add pressure. So the inlet comes in lower and the outlet pressure is higher. But in this case, the inlet pressure, like the absolute pressure, is actually below atmospheric pressure. So pulling water uphill is a really bad idea, because if you pull it up a large enough hill, then this rho GH term, the pressure, the decrease in pressure across the pump, will be actually large enough to create cavitation inside your pump. Cavitation inside your pump makes your pump noisy, it makes it full of vapor, and those vapor bubbles will eventually collapse downstream, destroying both your turbine blades, plus probably causing corrosion inside your pipes. So this is what I would call a bad design. If you need to get water up a hill or something like that, it's always better to put your pump on the backside so that your pump is pushing water uphill. Why is that? Well, if you think about it, like if your inlet is coming from, say, atmospheric pressure where you have like a pond or something, then the starting pressure of your pump is now atmospheric pressure, and on the other side, it's atmospheric pressure plus some extra amount provided by the pump. So in this case, we'll call that rho GH, the weight of your fluid. So that's enough pressure to overcome the weight of your fluid and send it uphill, where it then exhausts to atmospheric pressure. And in this case, everywhere inside this pipe, the pressure is above atmospheric pressure, and everywhere inside your pump, the pressure is above atmospheric pressure. So this is what I would call good design. You push water uphill instead of pulling it uphill. So that's sort of the importance of thinking about cavitation and vapor pressure as you do design.